Good evening. My name is Lewis Blackwell. I'm the curator of SuperMaterial, the exhibition upstairs, and this talk is a series of talks that we're doing with that exhibition. I'm also the strategy and development director of the Built Environment Trust, which is the organization behind the exhibition and indeed behind the building center. So thank you very much for coming. I think it's got a pretty interesting discussion we're going to have tonight. It's about a key aspect of what drives some of the thinking behind the exhibition, which is improving materials, finding materials that maybe do things better. In some ways, finding materials maybe that stories that we've lost and we need to rediscover and re-engage with. Now, our title, Harder, Lighter, Faster, Stronger. Of course, I could relate to many, many materials, and we've only got maybe an hour and a half tonight. So what we're focusing in on is the story of steel and stone. And we have some very interesting speakers to attend to what you might want to engage with around these areas. And it's not just what you see in the exhibition. We're going to be spreading, as it were, further the story. But certainly one of the pieces in the exhibition will be talked about, and that's on the stone side, where Steve and Pierre were talking at that. I'm going to introduce each speaker as they come up. So I'm going to begin, first speaker on our list here, Jitendra Patel. Let me read you a little bit about where he's coming from. So Jitendra is the Managing Director of International Metallurgy, and he's a consultant for CBM Technology Suisse. Jit is a chartered mechanical engineer, holds a doctorate in steel technology and an MBA. And he has 20 years experience in the development of high-strength steels with international steelmakers and marketing within the supply chain. And he's widely published, does a lot of workshops, training, and all-round expertise, advice in this area. Now, he's passionate about steel, and he's always been looking to strengthen relationships between industry, stakeholders. Over the last couple of years, indeed, I've certainly had plenty of insights of Jit's kind of thinking around this, and indeed, the CBMM that Jit works with were a fantastic support for the structure we did a couple of years ago outside the new house for London that was built out of 2 steel containers. Things didn't quite happen to plan, but they were a fantastically innovative, supportive company in making that project happen as it did. So that was the beginning of our relationship. And he's been telling me lots of interesting things since, and now he's going to share that with you and about what we should be doing with steel and where steel can go. A thing that we often think is a very straightforward material, actually has got wonderful potential still untapped. So what we're going to do is take questions after Jit's talk, and then we'll take questions, I think probably after Pierre and Steve speak, because they're going to speak about stone, and there's a lot of connection between their 2 talks. And then we'll bring everybody together and have a sort of general panel. So be ready with your questions, okay? So, Jit, please.
Thank you very much, Lewis, for the kind introduction and the invitation to give you 10 minutes of my life, effectively, of what I do for my day-to-day job. It was quite a broad topic, really, to get a challenge to talk about steel and where it comes from in this context for built environment and as a super material. Because I'm sure my fellow speakers coming up will also have the same predicament when they were putting their presentation together, because it's a lot of people think steel is old. We've been there, we've done it. What's so super about steel? And I think stone will have the same sort of questions thrown at it. So, but hopefully in the next 10 minutes I can give you a bit of enlightenment and hopefully thrust steel back into the echelons of Superman and super steel for you. So, to put it into perspective, I found an old photograph which was taken in June 1911. This is a picture of a steel beam, because we're talking about structures and construction. So a typical I-beam that was made, and this was made in Differdange in Luxembourg, which is now part of ArcelorMittal, which some of you may have heard of, one of the largest, or the largest steel group there is in the world. This was the first deep 1 meter high section that was produced at the time, and it was weighing about 314 kilograms per meter. So that was in June 1911. So you can say, well, we've done it then. That beams exist, and it is made of steel. But to put it into context, in 1911, approximately, the global steel production was probably in the region of around 15 million to 20 million tons per annum. And today, it is at 1.625 billion tons of steel. So that puts it into context. So when we start talking about super materials, I look at steel from saying it's widely available. It's produced all around the world. It's in our everyday existence with all the things that we do in life, with transport, with infrastructure, with energy. And it also is a material which is used when we make other materials or shape other materials as well, whether it's wood, stone, etc. So it's a critical part of our world and our life. Bearing that historical perspective in mind, when we look at the global steel industry, at that 1.6 billion tons of steel, you can split it into three areas generally. One is the top, which is showing pipeline systems, so energy systems. And there, the global usage is around 67 million tons of steel. Automotive, 216 million tons. And structures or construction is 833 million tons of steel, which is half the global output as a product. But in the industry that I work in, and I always a little bit give my peers a hard time as well in the industry, because the oil and gas sector, in particularly oil and gas transmission systems, large pipelines, they're considered high-value items, sophisticated metallurgy, because we're talking high-pressure gas pipelines in very cold climates in some cases, or deep down in the seabed. There's a requirement for high quality of the product. The orders are very large, can be. Cost of production is medium. So steel companies like this because there's a reasonable amount of profitability in it. And the same thing can be applied for automotive. In particular, the automotive requires very high quality of steels. It's quite an innovative area, and only the best will do. But when we look at construction, it's always the poorer brother or the poorer cousin of the steel family. And I always say to my clients, you know, look at the number. It's 833. It's a huge number. So why are we not giving it the love that we give, certainly with automotive, for example? So I'm always battling for the structural side because it has a poor image. It has that. A lot of people think that, both within the industry, but also the users of the industry. And one of my ambitions is, and passions, as you can see, is to change that perception. So one of the things we have is the usage of steel. It comes down to designers, architects, if you're talking structures. And this was a quote by Gail Haldeman, who was the designer of the Mustang, the iconic car. And he said, designing a good-looking car is absolutely easy as pie. Designing a car that a company can afford, the manufacturing guys can assemble, and the engineers can engineer is damn difficult. And it's still true today. And we see that with structures. So I guess some of you can guess what that is. Can we guess which structure this is? The Shard. So this was the drawing Sir Norman Foster penned. And that is the Millau Viaduct. So these were the drawings which the Millau Viaduct that Fosters and Partners did. And that had to be made into reality. And that was an extremely difficult project to make. And it was made predominantly out of steel, because when the project was initiated, FEAge had the contract to make it, and they had both design teams from a concrete view and also a steel division, and they put an internal competition to say, right, whoever comes up with the best way of making this to achieve that vision gets the contract. And in the end, they had to make it of steel because it was the only way they could make it to lift the decks that high above the ground. So, taking the cue from automotive, this is a slide from, again, ArcelorMittal, which is one of the leading innovative steel makers it's out there. But you can see from 1990, and there's a car from the 1980s, some of you may remember, there has been a lot of developments to modern-day cars that you see today, and that's the body-in-white structure, which you can see, where we're looking at safety, we're looking at impact, crash performance, because we're wanting the passengers, the occupants to be safe. So there's been so much improvements and designs of the steel itself in order to get fuel economy, to get safety, to save on the environment with fuel consumption, and also for corrosion performance. So there's a lot of developments that have been happening in the steel in the last 10, 15, and even 20 years. And when we look at a bit on the technical side, we can see here, this is the classic, what we term banana curve. And this is typical as what we would expect with steels. The higher in strength you go, the less ductile it becomes. So we see this banana curve. If we look back at that steel beam that I showed in the picture, it was probably a mild steel. Some of your cars, the outer body panels are made from IF steels, because the IF steels are very pure iron almost. So that allows you to create very complex and beautiful shapes, so very round or deep drawing shapes. So if even your Coke can is a deep drawing component. So we can make very complicated shapes. And then we start to increase the strength and the ductility starts coming down. But what we've started to do is push away from this natural boundary and to actually start making steels that are not only high strength, but also exhibit very good performance from a ductility point of view, which then allows us to make very beautiful shapes and provide solutions to certain engineering challenges. When we look at structural steels, you can see from the timeline, most of the steels we use today is around this, is the grade, we term grade 40, grade 50, some of you may know. It's a 355, it's 355, this is the yield strength of the material. So these numbers indicate when the material starts to plastically deform and starting to yield. So normally, from a functional point of view, we don't want to go above the yield point from once we've formed the component. So these are all classed beyond this higher strength steels. But you can see that a lot of these steels were developed in the 70s, but we're not seeing them being widely used in the structural community as we see with automotive. But this doesn't mean to say that we can't innovate with these things. So when we look at the steels today for structural, we can produce high-strength steels. We can produce steels that have improved ductility. We can have steels that are better weldability, because there's always an issue about all these materials need to be cut, formed, bent, joined. We have steels that have excellent cold temperature performance. So we have steels that will function below minus 50 degrees C, and you can hit it and it won't shatter. And even lower, because we have steels that are used for cryogenic purposes, so we're well below 150 degrees Celsius. We also have steels that can respond to seismic performance, because a lot of these buildings that we're seeing are in seismic zones. We have steels that have a certain amount of fire-resistant capability. That means they will hold their strengths to a certain time and temperature. And certainly in a building's point of view, that's very important, because it allows, the aim is to allow safe passage of the occupants of the building. We can have steels that are functionally graded. We can have steels that are transforming in their properties. So when you form the steel, the properties of the steel change and so I'm not talking work hardening where the steel gets stronger as you pull it, because if you get a piece of steel and you pull it and it starts to thin, it gets stronger because you're changing the microstructure. But we can also get steels that will transform its properties during certain conditions. And one of these steels is called trip steels. So it's called transformation-induced plasticity. So when you put a plastic deformation in the steel, you start changing the microstructure of the steel, which then adds further strength. And as you saw earlier, as the strength goes up, the ductility goes down. But in this type of steel, the ductility actually gets better. Steels are also part of composite solutions. We see lots of concrete steel solutions, which is a composite. And today, we're seeing lots of use for steels being used as rapid prototyping. So we're looking at steel powders, for example, producing rapid prototyping nodes. And there's a project which is currently being finished in Amsterdam where they built a bridge using a 3D printing technology. So there's a lot. Now, when we talk about structures, it would be remiss of me not to mention, for those structural guys in the room, is Fazlur Khan, who is really the father of and the pioneer of working and looking at steels being used in tall buildings. So he worked out that obviously as you go taller, the weight of the structure increases, but we also need to take into account the vertical, the gravitational loads, but also any lateral loads, which may be from things like wind. But the taller you go, there is a premium to pay with the weight of the structure. So the more weight it is, clearly the more steel you've got to use, or building materials you've got to use, and the bigger the foundations have got to be in order to take that weight. He designed and came up with various solutions of how we could use steel in the most efficient way. And over the years, that's developed from a rigid frame structure all the way through to what we term truss and tube. I'm not a structural engineer, by the way. I've got reasonable ideas of it, but apologies to those in the room that are structural guys. But we've got various systems which can be used for high-rise buildings when we're using steels. And here are some pictures of different types of systems. This is a diagrid system, which I think are very pretty and I personally like. So these are structures that are developed without a core, without a concrete core, because normally you can get a concrete core building and then you will have the steel coming radiating out and then the floors built around it, and you can have what they term as a belt and truss system. So this is a diagrid system. There's a very famous early diagrid system here in London, which is the Gherkin. If you look at that structure, that is a diagrid system. And this structure itself was developed, I think, in the 18-something by then in Russia, an engineer. It's taken off and adapted in modern day, where it basically allows much more space within the structure because there is no concrete, there's no central core system. And it also allows very intricate and beautiful design. So you can see there the Capitol Gate in Abu Dhabi, which leans at 18 degrees. This is a slide from the Council of Tall Buildings and Urban Habitat. And really, what you need to be looking at is the top right-hand corner. And you can see that as the buildings have got taller, we've gone from pure steel, which is at the bottom part, to a more composite structure, which is the triangle. So the taller the buildings, we've gone to a more concrete and steel solution that's required. So if we go back to steel, that's the periodic table. These are typically the main elements that are found in steel that we use. We have certain elements like hydrogen, oxygen, sulfur, and phosphorus, which we don't really want. They're residual or tramp elements, and we try to keep them as low as possible. But we've got carbon, we've got chrome, we've got manganese, and we've got some other elements which are here, which are the microalloys. And I'm particularly interested in niobium, which is element number 41 in the periodic table. And that, and I'll explain, is a very small addition of this element into the steel make will enhance the strengths of the steels in particular. And we're talking here levels of 0.015. So we're talking 100 ppm, 150 ppm parts per million. Okay? So typically a steel will have something like 0.04, 0.1% carbon, around 1.1% manganese or 1.6% manganese. So we're talking extremely low levels of this. So the metallurgy of the steel is done through grain size, microstructure, all these mechanisms, solid solution strengthening. This is what the metallurgists use. It's controlled by the composition and the manufacturing route. That together gives us the process physical metallurgy, which is what I do. So it's basically the cake ingredients, flour, eggs, how we put it together, mix it, how we bake it in the oven. So these are all the mechanisms which can be used and are the most important for the metallurgists when they're designing and when we're designing the types of steels. And this just gives a schematic. I don't want to go too technical because I don't know what the level is, but it gives us an idea. We reheat the steels when we make these slabs or ingots, etc., in the old days, and we roll them down to the plates or the thin strips that we see today, and we condition the microstructure, and then we cool the steel into various stages. And what we term here is what we term the transformation. So the steel itself has different phases of the microstructure, which then give us the properties that we desire. So effectively, what we're able to do as metallurgists is to basically make use of these building blocks. We have the basic recipe, and then we can add different mechanisms, which we have known about for quite some time. But as technology is improved, analytical capability in particular and processing, we're able to understand better and still push the boundaries of what the steel can do. So this is typically what we term a ferrite-pearlite microstructure. So this is what you would see with that beam that we saw right in 1911, typically. And this is still what we use today. We will still see this. But you look at the micron bar. That's 100 microns. We can start developing structures then a bit more finer, 10 microns, a bit more complicated, 1 micron. And now we start getting even further, 500 nanometers, 10 to the minus 9, okay? This is what we look at. We start to understand what is going on in the steel and how these types of microstructure gives us the performance that we desire. So just showing you some quick shots of microstructures. So there's perlite, which some of you may know. So we can actually start looking 10 nanometers with modern analytical equipment, exactly what is going on with the atoms and what's happening where. So when I'm talking about elements such as niobium, for example, we've got 150 parts per million, we're able to find out what is that particular element doing in the steel and what it's giving us. And this gives you an idea of the microstructure. So this is the steel magnified, and it's etched slightly so you can see the structure. And this is the same chemistry, the same cake recipe, but it's been processed in a different way. And basically, it shows that we can develop different properties with the same cake recipe, but depending on how we process the steel. And this is what I do. And remember, we're not talking small things. A typical heat of steel that we make is around 180 tons of steel or 300 tons of steel at a time, the cake mix. Okay? So it's a lot of mixture. And this shows the grain structure and the orientation of the grain. So again, we're able to understand which orientation and the plane that we want these grains to perform, because they give us different properties. It's like wood. You have a certain grain of wood in certain direction to others. And we can work out what we term as the angle of the boundaries, so the angles of the grains to one another. High angle grain boundaries, low angle grain boundaries. Which are better? Some grain boundaries are better to stop propagation of cracks, for example. And then when we talk at even a finer level, it irks me sometimes that we make a big issue of nanotechnology. Well, I hate to say it, but we've been doing nanotechnology since the 1960s. That's when we discovered it. It was happening before that, but we just didn't have a powerful enough microscope, and we just didn't discover it. But around the 1960s, we discovered the mechanism of what we term precipitation strengthening, which is where the element that I spoke about, niobium, comes into account. And what you need to know, basically, is those grains that I showed you earlier, the smaller those grains, the higher the strength of the steel, effectively. So that's good, and the toughness improves. We can improve the strength further by developing these very fine precipitates. And these are rows of precipitates that form during this cooling of the steel when we're rolling it. But we're talking nanometers in size. And they provide significant strength contributions. Look, 100, could go up to 1,000 if you get it right. And it's based on the fact that the smaller the size of this particle, and the more there are, the volume fraction, the higher the strength. And this was defined by two gentlemen called Ashby-Orewan relationship. And we can work out how much of this is going to go and produce those precipitates to give us the exact strength, roughly, that we need. So we can calculate that and make it into reality. And this just shows this looping mechanism of how these strengths are. I won't go into the science, but we get to this level of trying to design the steels which we use today and can be used today. So these high-strength steels, certainly from a structural point of view, can give us all these benefits of less material, because we're using a higher strength, so we use less material. It allows, or you can have a greater load-bearing capability. It allows us to have lighter structures, slender structures in some cases, reducing production costs, and reducing the environmental footprint. And this just gives an idea of, depending on the loading conditions of the steel, we're able to save 40% to 20% depending on the loading condition and as we go higher in strength. So clearly the higher in strength you go, the less steel or thickness is required. So you can save money on the steel weight, you save money on transporting the steel from A to B. You have to join the steel, so if it's thinner, then you need less weld material. And if, for modern steels, we use much lower carbon, so therefore the welding is a lot easier. Not only do we have less weld material, we don't have to do what we call preheating or post-weld heat treatment. Because some of these steels, the thicker the section, we have to heat them up before with the flame to get to 300 degrees, 180 degrees, and then we can weld it. Otherwise, we can get cracking of the weld. And if we can use modern steels with lower carbon technology, then we don't need to do that in certain cases, which makes things much more efficient and much more safer. Because if you're building a skyscraper that's so many meters up in the air, the welds all have to be checked. So how do you check the guy welding that at a very height, that piece of material is at 150 degrees at half an hour and the weld's been done properly and cleaned properly? So one example we did was with Arup. I did a project, and that was to redesign a structure which they were building in Mexico City, which is currently being built, the Reformer 509. And effectively, they originally designed it with a lower strength steel of grade 50, which was standard. We did an optimization study with them, I did, and looked at various elements of the structure to see where we could go to a higher strength. All of the seismic calculations were done, and we found that we could save between 45 and 35% reduction in the mass. And when we looked at all the elements, the steel library into this structure, we focused on the columns, effectively, the concrete columns and the pillars. And effectively, we saved about 6% on the steel alone, weight, which does amount to a few $1 million, which is very important for the owner of the property. And by going to a higher strength steel, we were able to reduce the column width, the size, so we're increasing the floor space area. So for the owner, that was a better return on investment. Or he could make or she could make the floor to ceiling height more because of the aesthetics were better, because we're able to have more weight within the structure to take more weight. Because if the columns get shorter and smaller, the stockier columns at the top, slender at the bottom, slender at the top, if they get smaller, then the foundations don't have to be so great. So we're saving, again, more money and more work, local work on the environment. So this is where we need to understand, my passion is saying, yes, there's modern steels, and we need to understand what modern steels can do. We also need to look at, where possible, where we can optimize our structures for high-strength steels use, because that's where we can see significant benefits. And we have to look at some of these very small elements, such as niobium, which basically allows, I call it, as a technology enabler. So often we have to look at not only the steel cost, but the chain. What benefits does it bring from the environment, from the welding, from the transportation? So not only the price per ton of the steel, which often people just look at and say, oh, it's a higher strength, it's a modern steel, it's going to cost a little bit more. Yes, it is going to cost a little bit more, but you're not going to use 1,000 tons, you might just use 800 tons, so there are savings to be had. That's me. We're still innovating. That's me with a customer of mine in Qatar. That's a 600 grade rebar steel. Today, we use 500 grade rebar steel, so we're able to make a slightly higher strength steel. It's been CARES approved, it was developed last year, and now we're looking at slightly tweaking that chemistry and the processing to basically make it a bit more seismic resistance as well. So we are still innovating on a product which a lot of people just is commodity. It's way old, isn't it? Rebar, everybody knows rebar, it's a very old product, but it is still innovating. Chicken and egg. So I'm just getting to the end of my slides here. I always put the chicken and egg because for those of you who use steel or are involved in steel in certain parts of what you do for your day-to-day work, I always say it's always a chicken and egg situation, a bit like from automotive, etc. Because as an engineers, we look for the best optimum solution because engineers innovate. I like to innovate. And when I talk to my customers, the steel makers, I say, well, why aren't you producing these fancy steels like we do with automotive? We know the knowledge. I'm not reinventing everything. I'm transferring the technology from automotive to structural. Yes, there are some little changes we've got to make, but it's not rocket science. So why can't we do that? And a lot of this, because there's 830 million tons of stuff for construction, they say, well, people don't ask for it because they don't know. So those of you in the audience that are using steel, ask for it. You know, we can do really sophisticated things, as I've quickly shown for automotive, for example. We can translate that to construction, to structural steels. Because the steel makers say, yeah, we can make it, but the customers don't ask for it. But the customers don't know that that exists, so they don't ask for it. They just get plain vanilla all the time. So, closing statements. Remember high-strength steels. If you're using steels, don't just go for the same old, because it's always been there from 1911. And remember that there are such things as elements, microalloying elements such as niobium, and the slogan we have and the strapline we have is grams saving tons, because literally is that. We're adding 1 gram or a few grams to 1 ton of steel, and we're able to save an awful lot, like 20%, 30%, 40%, depending on the type of strength or requirement of the steel product. So I'm going to leave it there. So thank you for your attention. Hopefully I've given you some food for thought.
Just step down there, just because if there's any questions right now, we'll take them. 2 or 3 questions anyway. One at the front here. Could you wait for the microphone, because we are videoing tonight. So is there a microphone in the room? Yeah, the microphone. It just helps you actually hear the question. This is the man in front here.
Sorry if I ran over.
No, not at all. Sorry. Okay, thanks so much.
Thank you for that. That was great. I've learned a lot of things about steel. Just a quick question. The steel's main competition is reinforced concrete frames. I would like to hear your opinion on comparing steel structures or RC structures. There seems to be maybe RC structures is gaining weight, especially a lot of post-tension structures are being used at the moment. So just wanted to hear your opinion on that. Okay.
I'm not a structural engineer. I'm a mechanical engineer and a metallurgist, but I have been working with people like Arup and WSP and engaging with those sort of guys here in London, in the UK for certain. A lot of RC structures also use steel because of reinforcement. Okay, so this is where, you know, as I said, it's a composite structure, so you can make use of high-strength reinforced concrete beams and rebar in there. So there are the biggest challenge I see, and I don't know whether it will answer your question, so I apologise, but the biggest issue we find is the availability and where the structure is being made. So in certain countries around the world, you can have, and I was talking to an architect in Singapore a few weeks ago, and he had a building which they'd built in Singapore, and it was made predominantly from steel. And there was an identical structure which the client wanted in Vietnam. And you just copy and paste, you would think. But the local skill set in Vietnam is not in steel, because they don't have enough welding engineers, they don't have enough steel contractors to build it. So there are certain things which then push the design or the requirement to be made out of, and in that particular case, he had to make it out of concrete, and he said it was bloody ugly. He said, you know, I didn't want to do it out of concrete, I wanted to do it out of steel because that was the best solution. But in Vietnam, it just wouldn't work because there wasn't enough people to make that project come together. They're very used to using concrete solutions effectively. So there is a trade-off. I mean, what I always advocate is saying, look, the best replacement for steel is modern steel, is better steel. That's what we do in the industry. We are innovating, we are improving the quality of what we produce to make it better and better. And we're looking at optimizing what we do. So we have to say, look, I'm not advocating everything goes to high-strength steels because it's not needed. But it's looking at the structure and saying, right, where can we optimize our structure through a combination of different types of materials?
Another question?
Yeah.
Hang on, let's wait for the microphone.
Just a couple of questions, really. Grams saving tons, does that save embodied CO2 per ton? That's the first question. Second question, was there an overall cost saving in the Mexico City project in going to the high-strength steel elements?
There is, the gram savings tons is obviously from a steel perspective, but equally it can be applied to CO2 point of view because, as I said, if you're able to save weight, then you're saving the CO2 from the emissions point of view, obviously from making steel itself, but also, as I said, from the supply chain point of view, you're able to save the transportation costs. So it's all the fuel side of things there as well. And I did a calculation, I did a backward case study, and I've done quite a few little things, so people, if my details are available, people can talk, you can come and grab me later or whatever, I'm more than happy to discuss it. But I looked at the Millau Viaduct as a case study, and they used some 355 and some higher strength steels as well. And I worked backwards and said, well, what happens if there wasn't any 460 or higher strengths and they all had to use 355, which is still a reasonably high strength steel in some degrees, in a sense. And there was, obviously, it would cost more because you need more steel to be used. But the most savings that were made on the cost of the project, and even a little bit on the CO2 side, was the transportation, the logistics of it. And we sometimes forget all of that, because the steels are made in whatever country or wherever, they're transported across. So there's significant savings to be made from environmental side as well. Sorry, and the other question you had was on?
Did the Mexico City power, was it cheaper in financial terms?
We didn't, unfortunately, when I did the project with Arup, I was in when it was a live project. So we had a certain time restraint because the steel had to be hedged from the guy buying the steel, sourcing the steel. So it was all done almost 18 months in advance. And luckily it was done before Trump, before the peso crashed anyway, so they got it built in time. But on paper, yes, there would have been a saving made on that. And I think it was in the steel alone was around between around $600,000 just for that structure alone of the pure steel costs. So I'm not even talking about any welding or transportation and craning, etc. So there are significant savings to be done. And I did some similar exercise in the Millau Viaduct, and there was 2.2. For my calculations, by going to a higher strength solution, they saved $2.2 million purely on the steel side. And I think we also, one of the key things, sorry if I can say, is for those on the environmental side, steel's recyclable. And we're also talking nowadays in the industry about reuse. So when a building has its end of life, we don't just crush it and remelt it. We could actually say, well, if we know what the beam is, where it's come from, we know the conditions that it's been loaded under, and if it's not been yielding and it's not had anything major done to it, then there's no reason why we can't reuse it. And it's an interesting discussion that's happening in the steel industry right now about data. And I was talking to one of the directors at Tata Steel recently at a conference and seminar, and I said, one of the valuable companies there are is Experian, for example. They just came from nowhere, and all they do is gather data. And the same thing will happen with materials, and in particular with steel. There's 1.6 billion tons of steel produced every year. A lot of it's going to get recycled for sure, and reused. Some of it's going to get remelted. So if we can understand and gather the data is going to be extremely valuable going forward as well.
I've got one more question, then we need to move on. So I think I did indicate, I'll take one over here, the chap in the middle here. Thanks. Thank you. But please keep your questions. We'll have lots more questions later. But one now.
Hi there, I'm a bridge engineer. I think we maybe need to have a quick chat about the Millau example you've shown. But one of the reasons we don't use as much high-strength steel in bridge engineering is to do with its fatigue properties. Bridges are very often governed by fatigue performance. You talked about new innovations. Is there any work to improve the fatigue performance, particularly of structural plated steels?
Yeah, on the fatigue side of things, and I appreciate the bridge engineers are extremely. It's a key factor, obviously, from a fatigue point of view, and for some of these structures. And there needs to be some revision of standards and specifications, which I also get involved with, because a lot of these standards and specifications were done in the 70s or even earlier, or when things went wrong. Standards and specifications were put together. And that was put together at the time when the steel industry, we weren't making steel so clean. We weren't making things with a much lower carbon within the steel itself, or the residual elements, these tramp elements, were quite high. So the fatigue side generally comes on the weldability side of things. So the view is that the higher the strength, then the assumed floor crack that you have in the weld metal itself is slightly more severe. And when you look at these high-strength steels, these high-performance steels, and you do a fatigue test on it, they do have a slightly improved fatigue performance. So the question is that we as a community need to get better data and get better information together for people like yourselves to use. Yes, fatigue is always going to be a critical thing, but it's not necessarily always the steel itself. It's going to be the quality of the weld. It's going to be how you prepare the weld and how you dress the weld afterwards, because there are fabrication methods which you can use, which eases any fatigue issues, and it's not necessarily the steel itself. And just one quick word, I know, Lewis, you want to hook me off, like the example I gave with the rebar. We're doing a lot of testing at the moment on that particular, because one of the things which I'm developing further with my client is making that higher strength rebar into a seismic grade. So we're looking at the low strain, low cycle fatigue phenomena on that. And the critical area of a rebar, when it fails in fatigue, is not the strength or the microstructure that you see inside the steel. It's actually where the rib geometry meets the main steels. And if the rib is wrong, or there's an issue with production, that's where the fatigue is going to initiate from and then propagate. Not the microstructure, it's the physical characteristics, the outer characteristics of the shape of the product. So it's those sort of things which we need to sort of understand and appreciate, and not necessarily say, well, high strength steels, poor fatigue properties, because they don't have very good fatigue properties, very good weldability as well in today's modern world.
Well, I know there's a lot more questions there, and there's a lot more information clearly in here that we need to get out. So thank you very much, Jim.
Thank you.
Round of applause there.
Thank you very much.
And we certainly will have a chance to return and ask more questions. But next, we need to move from steel to stone. And we have two speakers who are connected in the work they've done together. And we're going to begin with the man who's got his hands actually on the substance, on the stone, with Pierre Bidaud, who's a project manager at the Stonemasonry Company. And the company specializes in design, fabrication, and installation of natural stone fireplaces, staircases, and commissioned pieces, as well as restoration and conservation of existing stone. Pierre worked as a stonemason for 10 years around Europe, and has over 17 years' experience working in stonemasonry in the British Isles. And he really brings together engineers, craft workers, and architects with his traditional craft skills. So Pierre, please kick us off with stone. Here we are.
Right. Okay, so yes. So thank you very much for having me here tonight. It's a pleasure, and it's always nice to be able to, as you will see later, to share the love of stone. My parents must have been a very funny people. They are very funny people. Because they call me Pierre, and so I become stonemason, Pierre being stone in French. There is another, I'm just coming after you, which I'm not very good with numbers, so there will be no numbers in my talk, okay? And I tend to be off topic as well, so good luck with that. The other thing as well I'm known is that I like to annoy people. So, plus haut, plus vite, plus fort. I thought that since the Independence Day of the 23rd of June last year, we could have this discussion en français. Donc, dans un esprit d'entente cordiale, j'espère que par la fin de cette discussion, vous parlerez français. So, plus haut, plus vite, plus fort. It's Pierre de Coubertin, of course, and it's linked to the title of the exhibition. When I say sharing love, it's because it's been for me a very long time with stone. First, obviously by my name, by baptism, but I was dragged into Greek ruins for a very long time, and that's me. In Olympia, I was 7 years old, and that's me nearly 30 years later doing and working marble and doing marble bath. So when we talk about harder and stronger, there is one thing you've got to know about stone: it is very hard and you need to be very strong. So they inherently have this capacity, these things inherent capacity of being hard and strong. And when you look at stone, when you work stone, there is something about these 4 words that you've got to understand, is that you will have to be strong, you will have to be harder, you will become lighter because you are going to lose a lot of sweat working, and you are going to be fast because you want to make money at the end of the day. But the thing about this love of this material is that I was always fascinated by how this magical and fantastic building were made when I was visiting Greece or when I was going through France. And I thought to myself, this building do not exist anymore. You cannot roam France or Europe and find this beautiful building being built in stone. And I felt frustrated because I wanted to have the same pleasure of Gothic builders Greek or Roman sculptor or some other carvers in Phnom Penh to carve magnificent piece of stone. But I was born a bit too late, and that's yes. About stone, there is something you should know, is that what's beautiful, especially in the Gothic period, and I think I will describe later the sort of four aspects for me that's very important, these 4 age. And one, for me, the very first is the age of efficiency. As I say, strong is hard and you need to be strong. And so you want to use as less as possible energy to transform it, because especially in the Gothic time, it was man and some women labor, and you want to get the most of the stone with little as effort as possible. And this is, you are able to do that if you are using geometry. So geometry was very much at the heart of the design of this cathedral, but not only on the sort of sometimes a bit annoying thing of esotericism that can be associated with cathedral, but just on the way you cut stone. You don't want to move huge boulder of stone. That Gothic, if you look at the original, I mean, in my humble experience, if you look at the way they were built, especially the very first one, the most primitive first one, they used a small model of stone that was easy to manhandle, that was easy to transport, and that was easy to quarry. And then what you had to do is to do this magnificent vault. You wanted to use as light as possible material. So you had to be very good with geometry. And that is something that will come later on the discussion, but I think we need to go back to this age of efficiency. We need to be more reasonable with the energy we spend when we do things. Hence the work with Steve that will be talked later. Then there is the age of knowledge. Anybody knows what stereotomy is? Oh my God, that's fantastic. Can I take a picture? Stereotomy is the art of cutting volumes. Okay, it's a basic. I mean, it's not a basic, but it's the basis is that how do you cut volume using a two-dimension drawing? To do that, it was very much a sort of Renaissance sports. You know, you had geometry, you had biology. People in the Renaissance loved to soak in all this new knowledge. And one of this knowledge was, as I say, the stereotomy. The stereotomy is how do you get all the template to work, all this very tricky vault, staircase, squinch. I think you call that squinch in England. You don't have them. I think it's something you rarely that is in Lyon. That is a small courtyard, and they obviously didn't wanted this circular tower to reach the ground. So they did what they did. They did this sort of squinch, which was a sort of the penetration of a cone into this round tower. So it became very much, as I say, a sport, a sport of the mind, to deal with complicated and very tricky penetration of volume. How to get the best way to get a nice arrest penetrating here or here. So that's stereotomy, and as I say, it's very much a French and a bit Spanish sort of how do I call that skill. And they were put together by Philibert Delorme, a Frenchman, who decided to put that into a book. And after that, there were maybe 100 books all over France, Spain mostly, about stereotomy from the 16th century to the 19th century. The point here is that it's again about building beautiful shapes, being the smarter as possible with the material, because not only do you want to have a nice worked penetration of volumes and so on, you want the stone, you want to save as much as possible stone, because you want to be as quickly as possible on site. So it's not only a question of it's really a question of saving stone. So then, what I call the age of stupid, which is the Industrial Revolution. I know I'm not going to have friends here, but after all, it came. No. What I mean, the age of stupid is that we started to lose the plot. I think on the material side, especially on the stone side, is that we had big machine, we had steam to cut big lump of stone. We didn't care if it was going to take long, because we had plenty of machine working. Weight was not a problem anymore. You know, these are different pictures from the 1900s, and well, obviously the very tail end of the Industrial Revolution. But I was a bit late this morning digging all these documents. But what I mean is that we start to waste energy. People don't care about stereotomy. People just design wasting as much as possible stone. They don't care. So that's one thing. Now I'm going to try to do my best Steve Jobs impression here. What I mean is that I'm very pleased that I'm going to introduce you to one of the most dramatic development in our company, a completely digital piece of tool, an incredible piece of tool that we call CNC, but it's the B version. As you can see, it's a very, oh, sorry, it's the wrong one. That's our new CNC machine. It's a creature with a non-stop cognitive behavior. This young lady can shape a step, a stone, anything. I take the step of a stone staircase in 8 hours. There's no magic in it. It will be by a C machine. It will be maybe more time than that, as expensive as that. And I won't be able to discuss the last episode of Breaking Bad with every morning. And that is something that is very important, not the Breaking Bad thing, is that we have stonemasonry or wood cutting or blacksmithery. You've got to imagine that it's a culture. And we have a duty, us stonemason, any people working with natural material, to do our best to carry on this knowledge and not to have it just disappearing. And that's why at the Stonemasonry Company we don't use CNC machine. Everything is done by hand. But it doesn't mean that it's less efficient. It just means that we think that it's not where technology should be used to make things lighter, harder, stronger, faster. Yes, the digital edge. I'm very bad at puns, so that's digital edge, but it could be digital age. But digital edge. That's always make me laugh when people say we are in a digital time. Yes, we are in a digital time. That's called digit. Okay, that's a digit. So we've been digital for 60,000, 100,000 years. I don't know. It's us. It's not only our mind that makes things, that transforms things from metal and so on. It's our hand. It's our hand and our brain. And when I will just whiz through a sort of process of working stone. This is the copy of the Chanel shop stone staircase. We were commissioned in London, and it's got the typical French limon, which is a stone ribbon. We just go around the side of the stairwell to hide the side of the steps, and so that you can put a different way, a different handrail. style. You will see on the picture. So this is the traditional way, okay? That's what I called the stereotomy. It's how do you get all the template to use as little stone as possible, because you can waste twice the size of the stone if you don't know stereotomy. And all that was done using the digital machine. And I'll show you the process. You put your templates, you put your line with the different depth and so on that you need to use your cutter. Then you reapply another template to give you the different that you worked out on your stone. More. And that is the sort of stringer you finish with. Okay, that was 3 days of work. If you were going to do that with a robot, I would guess it would take much longer, because people only think about the bits that you put on the sewing table, but you've got all the travel of the tools to program into the machine. So it's not only the time on the machine, and it's so boring to look at the machine doing like that. I mean, I'd rather listen to Farage talking. Well, no, I think I'd rather look at the machine. Yes, yeah. So no, it's so. You see, you don't. CNC is not the answer for everything. It doesn't make things faster. We are as capable men and women to carry on doing that, to making things faster. But the problem we had is that us as stonemason, if we wanted to reclaim the way we used to build, the way the stonemason, the big cathedrals were built, big temples and so on, and big bridges, we needed to ask the engineer and their computer. What we needed was to bridge the gap with the craftsman. Okay, bridging the gap. Just again. And any talk about stone in France, you have to have a picture of Vanessa Paradis. It used to be Brigitte Bardot, but now it's Vanessa Paradis. So what was important is that if we wanted to make this new structure lighter and stronger, we needed the skill of, God, it's painful, of British engineers. I've said it. Just don't make him. No, just don't make him say it. It's I just. Okay. I think I've earned my passport. Come on. No. It was critical for us to move to some more challenging structure, to a better way to use stone, to team up with engineers, to work much further before the project began into what was the best solution. And obviously, it's now what stonemason in our company have to deal with in most of our staircase is just post-tensioning, which was a Freycinet invention, a French guy. So we are back on our track. So that's what look at the Stonemasonry Company now, a stone staircase with Webb Yates and his capable minions. We developed a new way of threading cable through stone elements, tensioning them, and then putting to some horrible things like that. I don't remember the load test was, but it didn't crack. And you can look at the thin waste you have here. It is, it's limestone. It's a reasonably hard limestone. Nothing too fancy. But we can go. Sorry. So there's just the stronger and lighter. I'm trying to stick to topic. So I just, if you meet my parents, you say no, it didn't go off topic. It stayed on the. Stayed on the thing. So faster. That was a project in central London, again done with Webb Yates and by the architect Aminta. And the idea was if we put 2 stone, and then we put a lintel, and then we repeat that, would that build a house? And we say, yes, we can build a house just putting 2 beams and then a lintel. Wow. And it's what we done. So we went to the quarry. We just purchased 90 tons of stone of 400 mil by 400 mil section by 2.8 height, and we just stacked them on top of each other with minimum work as possible. You can see here some of the face of the stone being cut, and some which has been split by the plug and feather, something that has been around for nearly I give you 4,000 years. Now, something that people don't think about, I mean, something that we are very bad, the stonemason, is talking about what we do. It's funnily enough, you talk about this architect just before, but do you know which that one is? Ah, thank you. It was Padre Pio. So it's Renzo Piano, incredible church for Padre Pio in south of Italy. It's made of natural limestone from the local area in Bari. There is a sort of thread system and post-tensioning that has been put in place, and you can see the scale. I mean, they are 50 meter long and 16 meter high, and they again are earthquake resistant because it was again on a high risk earthquake thingy. You can if I don't finish my sentence, you can finish it as you want. You just put a word, anything that comes, because I'm not going to finish it for you. That's you can be sure. So you see, one person onto this fantastic audience know about Padre Pio, and it's natural limestone. You have here some colleague of us who just built their own workshop using, because they are stonemason, they use the natural limestone to build their arches. We did these 2 staircase, load-bearing staircase, post-tensioning, very thin, very light, hard, strong, and so on. So let's finish with a bit of poesy. Because strangely enough, in the guild of journeymen where I come from, the stonemason are called the poet. At the beginning, I thought it was an insult because I didn't, I'm working stone, so I don't look like a poet, do I? So, but poesia in Greek mean to create, if I remember it well. And if I had to substitute the words of harder, stronger, lighter, faster, I would use the words of L'Invitation au Voyage de Baudelaire. It's French. One of these paragraphs, he finished it with "Là, tout n'est ordre, beauté, luxe, calme et volupté." So for the unfortunate people who don't speak French, there is all this order, beauty, luxury, peace, and pleasure. And I think it's with material, it's what the mission of people who architect, engineer, craftsman is, just to leave the place where we live in a better state than where we find it. I mean, that's obviously it's an old Athenian motto. But I think it's good to substitute with more elegant words to build lighter and better structure. And this is maybe not the most poetic structure, but it's 1890. It's a stone staircase. These are pieces of stone, 100 mil thick, and it's in the poorest district of Lyon. That was the workers' housing system in 1890, and it was done with stone. No question asked. No, it's light. It was easy to bring. It was in this case, as you say, it's where the geography, where you are in the geography, that's going to make your building, use certain material, and that was stone. So that's it. Thank you for your patience.
Thank you very much, Pierre. Definitely correct to describe a stonemason as a poet, I think. Now, we're going to take your questions with Steve's at the end. We're running a little bit late, and I want to get your talk up and get through that, and then I think there'll be some joint questions probably as well, so that's the way to do it. But, let me just introduce Steve. You can stand up if you want to get your slides ready. But Steve Webb, you've already heard him mention. Director of Webb Yates Engineers and also of Interabang, which is a multidisciplinary group. Steve previously worked for Whitby Bird, Sinclair Knight Mertz, and Santiago Calatrava. He worked on many projects, including the analysis and engineering of the Wembley Stadium Arch, as well as the structural design of Calatrava's turning torso tower in Malmo. Steve focuses on finding innovative structural solutions to problems, designing structures that look good and work well. And he's a visiting lecturer at Oxford Brookes, and also a structures tutor at the AA. So, Steve.
Thanks very much. Yeah, so we have an exhibit upstairs in the gallery, which I think is the culmination of a very long and experimental relationship between me and Pierre and our companies. And how long have we been working together? 7, 8 years? 10 years? Too long? Not long enough for me to learn any French. We started off in the beginning, actually, we'd been experimenting with traditional stone cantilever stairs built with timber. And it's a very simple principle that each tread of the staircase, you're probably familiar with it, it's a Palladian device, is fixed torsionally into a wall. The load travels from one tread to the other by the wall, preventing the tread from twisting out of the way. So we built a lot of staircases like this with Pierre, very traditional ones and also more experimental ones. And we noticed in the beginning of our relationship that we were interested in trying different things and experimenting with the different forms and trying to make stone something less than a kind of Georgian or reinvention of Georgian architecture. We did a lot of these stairs, and I think Pierre, over wine and napkins, told me that it would be expedient for him if he could design free-spanning staircases. All of the staircases that are built traditionally need to have a wall next to them for their support. So we began to play with post-tension stone. This was a very early experiment in this line. This is a bench spanning 3.2 meters. We used to call it a bridge, but unfortunately it's more like a bench. 50 millimeters of stone spanning that distance with 2 cables that run in a parabolic trajectory from one side to the other, supporting it. Very, very thin, built like this. The cables sit in these slots on the underside. And these are the guys that made it, very proudly. Stone is superior to concrete. Concrete is chemically very similar to limestone, but actually stone's much stronger. Limestone's much stronger. And so as a consequence, we found through experimenting with this and through doing the calculations that we could make much thinner layers of stone span much further than concrete, and make very effective, thin, lightweight structures. So we did various staircases. I think we started with a 60-degree helix. We started with a straight flight and a 60-degree helix. We gradually built up the sweep of the helical stairs through a number of different tests and experiments. So this is the staircase that we finished a year ago. This is actually 1.5 meters wide. There's a kind of embarrassing balustrade to go on that subsequent to this photograph, so we sent the photographer in beforehand. But this sweeps, I think, 320 degrees. 320 degrees, and the treads are 1.5 meters wide. So we think this is a penguin pool-esque achievement. I think it's 125 mil deep in the middle, 2 cables with about 12 tons of pretension on each cable. So we began to realize that you can achieve quite a lot in stone. So each tread is solid. Each tread is an individual stone cut by the barbarians, batted up to each other with mortar. This there is unreinforced. This is not one of Pierre's. He's going to be annoyed that I'm showing this. Sorry. We're also interested in what you can do with stone that isn't reinforced. I think what we've achieved with What we've achieved with Pierre with the post-tensioning is fairly modern, but actually what we achieve in stone in general is very humble compared to what was achieved in Gothic architecture, Gothic arches. And I think we're relearning a lot of the knowledge and the skills from that time. But this staircase was a simple arch and an interlock of travertine marble without reinforcement. And we were enjoying the challenge, actually, of what you could achieve with stone without reinforcement. And from that, through a number of other, I think we've done hundreds of staircases, I think, in different structures, but mainly staircases, I have to say. But we were really interested in getting out of staircases and designing buildings. So this is the first building that Pierre showed in his presentation, but this is a Revit model of the building. It's a concrete frame structure. The concrete was built without any columns, built very quickly. The back propping in the concrete structure remained after the completion of the concrete frame. And then Pierre and his colleagues arrived and started building in the stone facade into the face of this building. And the stone facade, in the end, carried the load of the concrete frame. So this is we're certainly not the first people to do this. There's a similar building in Finsbury Square. But there's something very arresting about that. And I think when Pierre's talking about poetry, we'd like to inject some structural poetry into our buildings. And the idea that a facade that looks like this is actually supporting the building, I think gives something extra, some extra content to the architectural move. There's a lot of stone. I gave a talk a few years ago here, and somebody asked me what's going to happen when all the stone is used up. So we're promoting using more stone, and we think stone is a good material to use. There's a lot of stone down there. If we use all the stone in building, we're going to be floating around in space in office blocks, which isn't hardly feasible. Stone is, so stone's very strong. As I said, this is a comparison between typical granite and limestone and concrete. It's far superior to concrete, and it's just sitting in the ground underneath your feet. You don't have to make it. So the idea of digging up limestone, crushing it, and turning it into an inferior material, to me, seems to be somewhat illogical. It is a natural material, so we tend to have to allow relatively large factors of safety. Now, there's not much, I think, the level of investigation and science that goes into steel production does not go into stone design or stone analysis. So at the moment, we take a very crude factor of safety of 3. It's difficult to tell where there are flaws in the stone, so we have to account for those. This was a sample that was tested at Sandberg's. In this case, this ammonite is at the worst point within the sample for reducing the stress. It's invisible from the outside, so we have to kind of account for these sorts of things. Stone is very low carbon, and this is the important thing, I think. We did a comparison between different building materials, steel, concrete, timber. Actually, of all of those, stone, carbon footprint as a ratio of strength and stiffness was lower than any of those. I think something like 10% of the carbon footprint of concrete for reinforced stone. Because you don't have to process it very much. You dig it out of the ground and you cut it up and you use it. You don't have to dig up the chalk and the clay and process it. It doesn't have very highly energetic processes in its manufacturing. So we started thinking about how we can build with stone. Gothic cathedrals are very nice, but nobody's going to build an office like a Gothic cathedral in this day and age. Arches are great for stone, but we started to think about how we could develop things that would compete with concrete as a flat slabbing material. So this was an idea. This is basically a stretched stone cantilever staircase. If you imagine the treads are extruded, or rather like a tile puzzle. If you move a tile puzzle around, it hangs in an inverted shape because of torsional restraint of each individual piece. So you can keep building, holding the ones down in the corner, building subsequent pieces. You can keep building this and building this and building this if you have some kind of beam or wall support. So you can build a flat stone slab, no reinforcement, literally as if you built one stone staircase against another. So we have got into the rather bad habit of using museums for laboratories, which I think we're very lucky to have done some of the time, which I'll find out in a minute. This is in the V&A. They asked us to do an exhibit for the engineering season. This is a 40 millimeter thick limestone slab. It spans 3 meters. It's supported around the edges. The steel clips hold the corners of the stone together, but other than that, it's unsupported across that distance. So 40 millimeters thick of stone carrying a domestic floor loading, just stone, no cables, no tricks, no nothing. Carried our weight. I think this is an interesting potential solution for flat slab flooring. It's very redundant. The structure works in lots of directions. If you break one stone, you have to break a lot of stones to actually create a failure within that thing because there are 4 corners. Okay, this was a fabulous animation showing the revolutionary building system that we're exhibiting upstairs, which isn't here. So I'm going to have to explain it. But this is the piece upstairs. We're developing this on a shoestring. It's just an idea at this point in time. But the idea is that you might deliver individual pieces of stone. These are 400 millimeters square with a standardized notch and a connector. You can deliver 400 millimeter lengths of beam. These are post-tension beams, so there are cables running through there, and you can make a similar modular unit for the columns. So you can make 4 beams, 4 columns, several stories high, and infill that with flat plate stonework in the way that the V&A exhibit works. So the idea is that instead of having a concrete truck, formwork, false work, reinforcement, all the things that go into reinforced concrete, you could deliver a set of these pieces, standardized pieces, and you could build a building with them, and you could probably retrieve them when the building was finished with and use them somewhere else. These pieces of stone, because they're working in tension, you never use concrete in tension, because they work in tension and in shear, they're much thinner than their equivalent in concrete. They're much lighter. The finish is more interesting. We employ people in their making, maybe not a CNC solution. So I was very pleased with this. And when it was finished, I was standing on the end of there showing off how clever this solution was. But I can't not show you that it didn't quite go according to plan. So this is a lesson about doing things in a hurry, and doing particularly museum exhibits in a hurry. I made a mistake, actually, with the corner connection. The joints are fixed by a steel cruciform, and because of the geometry of the cruciform, the plates hold one piece of stone against the other. And actually, I missed that we cut the corner cruciform around a steel bracket, and so it didn't work. But we built it again, and now it does. So we're all on for the future. That's it. Thank you.
Thank you, Steve. Thank you for being so full and frank there. And maybe there were some more questions about that. So I'd like to invite all the speakers to go up to the front here, and we can take some more questions. And while you're getting over there, I just want to thank Trimo, who, by the way, have been sponsoring this whole series of talks, which is why all the tickets are free. So let's thank Trimo. They do fantastic systems of things, not actually for structural stuff, but some of the materials being used in the new Apple headquarters in California, Trimo stuff. So very high-tech company. Also, what was I going to say? Before I forget, there's a big article all about the work of Steve and Pierre and some of the stuff that's been talked about here in the new journal that we produced, which you may or may not know of, B. It's for sale at the front desk, or you can get it from our website. And there's lots of other wonderful things in that as well. Some of the other things are connected with talks we've had, and certainly a big piece all about the SuperMaterials project. So now to the questions. I'll kick off with one. I mean, get the questions ready, but I'll just try and bring the 2 parts of this together, as it were, 3 parts, but there's two materials. What action are we sort of thinking we need to see here to get sort of innovative thinking in how we use the materials? In both cases, I got a sense there was a problem with sort of education, with knowledge being transferred. In one case, knowledge being transferred in the past, being lost, and now somewhat being rediscovered and being advanced again, but getting it back out there, getting a sort of full embrace of what's kind of known, but is actually not in the system of building. There's a bit of a hurdle, both in stone and in steel, clearly high-strength steel. You know, why do you want to do that? We do it this way. And in stone, well, you seem to be doing things incredibly innovative, but actually you're doing things that have been done in the past. They just be a big deal now. So, can you speculate? What do we need to do to really jump onto these interesting ideas and this interesting potential of materials?
Do you want me to? I mean, I think specifiers of material, or any material, steel, high-strength steel or stone or anything else, depend on codification for their safety and design. They depend on norms and standards of design and manufacture and construction being in place. I think we quite enjoy the fact that there aren't codes for stone, although not always. But I think actually codification within legislative building control systems, that opens the door for use of innovative materials, but it lags a long way behind their introduction or their adoption. So particularly in the case of stone, and I suppose in the case of high strength steel, having a kind of set of codes that are contemporaneous with technological developments would really open things up in a way that.
Do you want to come in?
Yeah, I mean, I think I'd echo those comments, and the example I gave with the steels that are being developed and used for automotive industry, you know, they're years ahead of what we use in construction, and because the automotive industry is driven by legislation, by governments, because we want to make more fuel-efficient cars. There's a certain requirement for better crash performance. You know, we have 5-star ratings on cars for crash tests. You can have 2 stars. Nobody's going to go and buy a 2-star rated car. Everybody wants a 4 or 5 rated car. So, you know, it's behest of governments to put that forward, which drove the automotive industry. Otherwise, the automotive industry would have quite happily carried on building heavier cars. Fuel consumption's not an issue. So unless you get measures in place which force the industry to go down a certain path, which allowed all this lightweighting to happen for automotive, then it's difficult. So I think I agree. There's issues of revision of specifications and norms. Like I said, you know, a lot of the specifications we see in the steel industry and the usage of steel is based on standards and specifications that was developed 30, 40 years ago. And technology's moved on, and how we do things have moved on, and so those need updating. But equally, for the construction industry or structural industry, they also need incentives in a way, almost like a carrot and stick approach of pushing the industry to use more modern materials or innovative materials, or even older materials potentially. As you said, you know, why are we doing with the concrete? You know, we can do certain things with stone, exactly as you said. You know, we're getting a piece of block out the ground and grinding it down and then making it a concrete. And so we're creating more problems for ourselves. And one of the things, you know, we could look at is that with structures, we have things like LEED accreditation, you know, and green building, sort of kite marks type of thing. And it's big in this country, in the US, in Southeast Asia, where I do a lot of work. And one of the things governments could do is to say, look, if you're building a new structure and you can use more innovative materials, and yet you can show that the carbon footprint is reduced, then your rates are lower, or something's lower. So it encourages, like we have with road tax, right? If you have a pure electric car, you pay 0 road tax. So why can't we put in measures which will then reward people to go down that road, but also then encourages as well? So I think we need to be, you know, we need to put pressure back as well of how we can change.
Yeah, the other thing is, it happened in development of humanity. I think we tend to get on a sort of route with our life, our evolution, and then when we look back at some only small aspect of the past, and we tend to worship the past or look at it under a romantic eye, when really what we should do is looking back, saying, hey, whoa, what are we doing? There's no other way that was been done in the past that made things more efficient. The fact that they were working on a much smaller slabs of stone is very interesting, because there is less waste. You know, you've got to work with what you have, and I think it's that we, especially in the 1900s, we just there were a sort of laziness It's because the machine were there to cut this big block of stone. So we didn't care about wasting stone. We didn't care about the environment and so on. But now we need to be more and more careful about the way we used some of our resources. And if we want to look at the past, as I say, it's to look at the interesting bit of the past, not the romantic bit of the past. You know, not and that I think is that's why in the last 20 years in France, they with the creation with the writing of the Encyclopédie des métiers, the encyclopedia of craft, we came across so many new treatises in some old libraries and just started to find some interesting old way to build.
Okay, I've got 5 questions from you, Ralph. Who's going to be first? Up in front of you. Let's wait for the microphone.
Hi, I'm a structural engineer. So I've got 2 questions. First question, steel. Can you make, is it possible to make steel with a different density or a modulus? And second question, sorry, for stone experts, I think the video or the picture of the collapse was very interesting in that it was rather catastrophic. So is disproportionate collapse an inherent weakness in stone? And do you have a solution for that?
Go first.
Yes, to answer your question is no. If it's always been said that if you could find a way of changing the youngest modulus of the steel, then you'd be a very rich person. There are slight changes you can make, but not to the level that we would like to happen. Regarding the density is fairly standard again, and the only way you could really change the density is obviously if you're using much heavier elements. And when you look on the periodic table, the heavy elements tend to be quite nasty, so we tend not to use those. So unfortunately not, but from a construction point of view, it said 355, 355 megapascals, or the old grade 50 yield strength, is from a structural point of view, it actually has excellent strength to weight ratio, and that's why it's a very popular building material, which is why I'm not saying everything goes to a higher strength, but it's where we can optimize the structure with the right type of materials, then we can gain a much more efficient structure. But if I could just add, if I may, the 355 grade, for example, steel, which is here predominantly used today. So if you went to a steel industry in the UK or anywhere in Europe and said, I want a lower strength steel for construction, it's now a special order because it's not the norm anymore. In the old days, 275, or the lower strengths was, as we class it today, was produced every day. And today now 355 is the stock material in Europe and certainly North America. But even with that grade, I mean, I'm talking to users of steel, and I'm saying, and it's like I said, making a cake, it's like saying, right, like I said, this carbon is one of the critical ingredients in steel, and so, because it gives us strength, but it's also very brittle, and it causes problems with welding, so we prefer a lower carbon solution. So you can have a 355, I go to people who use steel, and they say, look, we bought this, and we bought this, they're exactly the same specification, but this one, it gives us problems in welding or cracking, and this one doesn't. Why? Because the carbon is lower. So a lot of it is about educating the user and saying, look, just don't go and order the steel on the piece of paper because that's the specification. It says 355 and you go to the steel maker or the stockholder and buy it, because you can have a 355 which meets spec, that's got high carbon, and you can have one that's low carbon or processed, made in a different way. But that one is actually going to be better for you from a processing, from a use point of view. So this is about being informed, and this is a lot of what I do, is actually informing the supply chain, because then they can make an informative decision about saying, right, that's what I'm buying, and I know why I'm buying that and what's in it, not just, oh, it's a piece of steel and I can go ahead and use it. We need to be asking the second and third order questions a little bit more, I think.
Stonemasonry question.
Yeah. I mean, this fell down so traumatically because of a very specific cock-up that I made, which wasn't obvious in the beginning. In reality, we would never build a two-sided structure like that because it depends entirely on one joint in the corner. When you build a four-sided element, actually you have to lose all four corners concurrently for the thing to collapse disproportionately. So the way that structure is divided up into segments actually mitigates against disproportionate collapse because you can have individual pieces failing without a total collapse. This is built like that partly because we didn't have that much space, and secondly because I'm trying to do something fancy with a big cantilever to impress everybody, which is not quite the
Steve,
result of
don't
what
stand on it again.
The thing about how to find flaws in stone, of course, when you extract stone, and how you extract stone means that you are going to go through a process of natural selection. When it comes from it's taken out of the quarry, there might be some heavy machinery. There might be some. It used to be extracted using black powders and dynamite. So you can imagine that only the best were going to survive that. Then after that you had the transport. That's why the stone coming from France, we had some breakage happening on the lorry, and that's why I'm against the change of the infrastructure of British road, so that the more rubbish the roads are, the better the selection of the stone will be on the lorries. So if you see a guy with a pickaxe doing roads, it's me. I'm just doing holes for the testing of our stone beams. But so yes, there is a process in place, but it's always frustrating for you, Steve, because you always want a sort of pure material. Or the purest as possible.
Well, I don't.
Or the safest.
We want a safe material and we want a consistent and reliable material, which currently we don't have. So I think the innovation in stone is not going to be in the stone itself. It's going to be in the control of the flaws in the stone, and actually they automatically grade timber or electronically grade timber, a process that X-rays the stone to find the flaws, or ultrasound or something which is scientifically beyond me, I have to admit, is something that would really revolutionize the use of stone in construction.
Question, yeah.
I'm a structural engineer, and I wonder if patience has something to do with the use of innovative materials, and I wonder how you convince your clients to take that extra time to say, we're going to analyze this further, because sometimes project managers want 10 stages in 2 weeks. I wonder how you convince your clients that maybe this is a good route to go down.
I mean, personally now, with age and wisdom. Wisdom. Yeah, wisdom. I'm able to tell to people, look, it's a Jurassic stone. It's 135 millions of years. I'm sure you can wait a couple of weeks. So yes, I mean, it is a problem. I mean, seriously, yes. On some of the structure, in the last 2-3 years, we've gained a lot of knowledge on answering this question. So now we are getting more and more. We only deal with certain quarry. We have partners that we can trust to deliver the stone of a certain grade and quality. So we are streamlining. We are shortening the development and design. But if some clients want some fancy stone where we don't have any data, yeah, we'll have to tell them, you will have to wait 4 or 5 weeks. I mean, 4 or 5 weeks, for God's sake, to test the stone in laboratory. But it's okay. I think it needs to be done in a nice way. We're nice people.
Yeah.
One or two questions. In case of the high-performance steel, what sort of cost hit are you likely to be taking by going down that route? And maybe, as architects, we should collaborate with motor manufacturers to use their steels. Is that an idea? And on the stone, have you looked at the Gustavino vaulting as a way of using the stone?
Okay, let's go first.
Okay. Yeah. You said on the cost, was it? Yeah, I think the examples I showed, there are cost savings to be made. As I said, like the Millau, I worked out that is from my calculation, back calculation that I did, because that was already optimized. So I just went to say, well, what happens if the higher strengths wasn't available? They use 420 megapascals in some of the box fabricated sections that they used for the decking. It was about $2.2 million was my calculation, and a lot of the savings were actually on not only the weight savings, but as I said, on transportation, because it had to come from 2 steel plants. And then I made some other estimations on welding side of things as well. So as I said, you're instead of welding a 80 millimeter plate, you're welding a 60 millimeter plate. So you've got less weld metal as well.
Depend on the scale of the project.
Sorry?
Does it depend on the scale?
Yes, it depends on the scale of the project. And the thing is, with structures, it's a bit more complicated because every building is unique, whereas every car is the same, in the sense of the model is the same wherever you buy it in the world. And that's one of the challenges which we face, because, and it's similar. It's interesting to hear your comments from the stone point of view, because, and the earlier question as well, it's because, as I said, steel is, it's 1.6 billion tons of steel. It's 1.6 billion tons of steel every year. That's a lot of steel, and we're building all around the world. And so, from a constructor's point of view, they need, like, you want consistency of material. So from a builder's point of view, they want consistency of material. They want availability of material, and from anywhere around the world, wherever the project is. And so you need to be, and this is where the specification and the standards come back into it. So you can go anywhere in the world and order a piece of steel, and it should be meeting a minimum specification. And that's the challenge which we face, where we can push a lot of new innovative materials, but at the end, and we can see lots of great ideas, not only with stone or steel, but other things and other inventions. But unless it's mass available to the masses and easily available, then it won't take off, because it needs to have a critical mass. Otherwise, people won't take the risk. They'll take it for unique projects, individual projects, but if we want it to really go forth and multiply, then a project will say, right, like the pipelines, for example. They're building, one of the largest pipelines they've built in China in recent years. In 2004, 2005 was the East-West gas pipeline. High pressurized, high strength steel, very, very demanding qualities and requirements. It used a couple of million tons of steel. It's 4,500 kilometers long, the main trunk pipe. So it goes a long way, and you've got spare lines as well. So the people then have to buy the owner of the pipeline. He then signs off the project. They then have to have the pipe mills to make it. So there's only limited production at each mill that can make the pipe. Then they're going to have to supply the steel plate to make the pipe. So again, there's only a limited number of mills to produce the plate in the time frame. So you've got an issue of, can you get the material in? It could be available, but if there's only 4 people selling it in the world, are you going to take the risk and put that on your order form and then have the liability that the bridge or the building or the staircase isn't made on time, because you'll get penalised? And so it's one of those things that we need to sort of start getting over. And it's that chicken and egg thing. As I said, the more people ask for it, the more the industry is pushed then to say, right, there's a demand, therefore it's worth us going for. And and that was in the steel industry, was the same. As I said, 40 years ago, 275 was the standard material. And today, 275 yield strength isn't available. It's 355 is the standard, and you've got to pay extra for a 275 because it's a special order. So we're getting to that stage with steel in certain grades. But again, it's about how people are informed. And I guess in certain industries, I know the steel industry, they're terrible marketeers. They're terrible. They're very good at making steel, but they're very poor at selling it. There's only a few companies that really know how to sell steel properly, and Arcelor being one of them.
What's there a stone part of that question?
The vaulting thing. Vaults. Philippe Bloch is the vault meister. Gustavino are bricks, aren't they? But I think like a Catalan vault.
Yeah.
Philippe Bloch has developed a lot of analytical technology around designing vaults. It's a Rhino vault, all those things. And I think he's doing really interesting things. And a vault's a really efficient form, and it's a perfect form for stone because it's all in compression. It's just not a very usable form for buildings. So we are pushing the other way to try and make stone work flat rather than arched. It would be easier to make it arched.
What sort of sizes and dimensions is it for like a 100mm slab? How big could you go? 3 meters or something?
Well, in that case, I mean, we looked at a theoretical design for a 7 by 7 meter grid, and the stones were 125 mil thick. So in concrete, that would be 200, 225, something like that. So much lighter. But that's flat. I mean, that's.
Any more questions? We've had one, haven't we? We have one in a second, but this one over here first. There's two actually. There's a lady in the front here first, and then there's a man next to her.
Yes, my question relates to the life of the buildings. Does the super steel, the strengthened steel, extend the life of, say, the shard, you know? And then the other question is on the, well, obviously granite is eons, but what would be the life of that one, you know, that the one there, and also what is the life of the limestone staircase, and would it wear in the middle in time?
It used to wear so badly. It's because people used to have much heavier shoes, and no, you know, come on.
I fell down once and in school. So
Yes, no.
I remember it.
Yeah. And now you don't fall on stairs anymore. No, I mean, limestone, Portland limestone tend to wear a bit more. As I say, the shoes quality was something to do with it. You look at the scullery staircase in all the places; they are much more. They were a lot more used. But as I said, the traffic and the shoes were a problem. About granite, I mean, I'm playing with, there's no granite, that's flint. That was badly napped, but it's going to be there for a while. A granite house, that will take a while to disappear. People don't. I mean, that's the beauty of thing. The beauty of stone is that when you hold a piece of stone, when you touch a piece of stone, you are touching what I call fragment of time. You know, it's a fragment of time, and you can, and after that, there is so much energy that's been put into the stone, into the billion years of fabrication, and then after that you come with our little mallet and chisel and put another 40 hours on it, and that's it. And Bob's your uncle, you say, I think, in English. And then Bob's your uncle for another 2 million years for the granite. Limestone, well, I give it a bit less, yes. But
I mean, the weather.
But we've got a good warranty.
The weather is any structure that you throw open to the weather will be destroyed really quickly. I mean, the weather destroys mountains, and I mean, in this case, like frost and freeze thaw, and actually the steel in this would be the weakest link because it would corrode quite quickly.
But if that's inside and you have granite outside, I mean, that's, it was the length of.
Yeah, I don't think. I mean, if you weather, I mean, almost every material, if you weather it properly, it'll last forever. There are 1,000-year-old timber buildings.
But I mean, would your the connections, would they wear out after a while?
No, they wouldn't wear. I don't think. I never thought about that.
The steel is, I mean, if you go to a higher strength steel, it doesn't. It's the design of the structure, you know, and it's about optimizing the structure. So you can. There's going to be no difference in having a higher strength steel, which will say, oh, will be there for longer. It'll be there for whatever period that it's been designed to be built for, you know. So the only thing you could say is that if you went to a higher strength steel, even you could use the same thickness, and therefore it'll be stronger. But from a building point of view, it's designed on the fact that it's not going to fall down. And so you've got, you know, it'll stay as long as you want, as long as, you know, you've got environmental conditions and obviously usage conditions, which will take its toll, but that applies to all building or building materials. But as I said earlier in my talk, what we're seeing today is most buildings, and you probably won't like me saying this, but most buildings nowadays aren't designed to be there forever. You know, they're not. They're designed. You know, if you go to Singapore, they have a policy that after 20, well, even less than 20 years, they will deconstruct a building physically, and it's perfect. Perfect. Yeah, exactly. So the whole purpose is that, you know, society moves on, but also you're able to update the material, update the technology and the resources. So, and that's the way cities like, for example, Singapore, keep themselves at the forefront of you know, one of the leading cities in the world, to attract people, to attract investment, etc. Is that the way? Because people move from one block to the next because the building suddenly got 10 years old and they think, oh, it's dated, it's terrible, you know, and they deconstruct it physically. And here with the steel, like I guess with other materials, you have the opportunity that if you understand what's gone in, what loading conditions where it's come from, the history of it, the loading conditions that it's experienced, the service life that it's had, there are possibilities to have a reuse, not just sort of remelt it or grind it down and put it into something else. You can actually reuse the girder, and there are examples now we're seeing, certainly in the steel industry, where they're taking materials from old aircraft hangars and things like this and reusing it in certain areas, or you're literally picking it up and redesigning with those elements. So it's happening, and it will be happening more, I believe, which is why I went back earlier and said about that. Some people may know about the Industry 4.0, as they're calling it, from the digital side of things. You know, that I think is going to start to play a big role in construction, in the construction sector, and yeah. Steel industry is starting to get to grips with it a bit, but it's going to come in a big way, I think, because it's data, and data is going to be very valuable.
2 more questions.
What would be the challenges of making high-strength steels using recycled steel compared with virgin material?
None. When you recycle steel, there are a few elements in there which people don't want in there sometimes, like copper, for example. So copper's a big issue from a steel making point of view. Copper's very useful from a corrosion point of view. So we do have grades like Core 10, which are trademark names, but you know, Core 10 is effectively steel with a bit of extra copper in, and copper gives that barrier because it gives that slight rust-coloured brown colour you can see on some structures, and in our railway infrastructures, for example, use a lot of Core 10. And that provides a protective barrier, an oxide layer that acts as a barrier. But from a steel making point of view, often we don't want to have too much copper in there. So we have to look at other ways of getting that out from a processing point of view. But generally, all steel is 100% recyclable. But yes, as we put more elements in, clearly, then you will always end up having that being introduced back into the recycling, into the chain when you're recycling. So yeah, those elements start to increase, the residuals start to go up a little bit more. So yeah, we have to keep an eye on that, but there's no barriers from a recycling point of view.
One more question then, you next in line.
So for the industry to use the new materials is a double way. The councils need to be educated so they can put it in a planning permit, maybe, as a carrot or a stick, and then the designers, architects need to be educated in parallel so they can get things done. And for the stonemasons, that was very, very interesting. You essentially do anything from a limestone to marble granite. Is your work standardized? Can I use your results to prove something in an environmental study, or?
You mean like an environmental performance carbon footprint of the stone?
Yeah.
I mean, it's really difficult to work out what the carbon footprint of a piece of stone is. There's a thing called the Bath Carbon Inventory where they have a list of different building materials, and they have an allocated CO2 footprint for general stone, for example. And according to that, stone is very, very low carbon compared to per strength compared to steel or even timber. I think that people find it very difficult to benchmark the carbon footprint of building square meters, for example. So they don't say, for example, the average building in the UK, when constructed, had a carbon footprint of X per square meter. If you build this building for half of X, then we give you some benefit, for example. And actually, as the building systems and the insulation of the building become more effective, the frame is a big issue. So there's that building in the south of London with the 3 big air turbines on the top that never do anything, which has thousands of tons of steel in it. And I'm sure when they opened that building, they were screaming about how environmentally friendly they were with their fans and their other novelty measures. But actually, the building itself is thousands and thousands of tons of steel, which is thousands of tons of carbon dioxide. And I think that the regulation of the carbon economy just doesn't have the sophistication to deal with the high level of variability in the building materials and any kind of benchmarking of buildings to be able to say, yeah, your building is 10% improvement on the standard. So it's much easier to go for building systems and air conditioning insulation first. So I guess at some point that will come, or at least maybe taxation will make high energy materials much more expensive. I mean, we're kind of pushing the stone thing because of its low carbon credentials, but there isn't really, at this point, a massive commercial advantage in using that. There's a moral advantage, I suppose. But I think as taxation starts to attack energy usage, then it'll become expedient to find materials that are stronger and lower carbon.
Okay, well, I'm going to put things to a close there. I'd like to thank the speakers for 3 very different and I think all 3 were very inspiring talks. The challenge, of course, is now how we can take that inspiration actually, as the last question really probed, and make some use of it. So that's the challenge. But it's been a great evening to hear this sort of insights, and it hasn't stopped here yet, because in a way, if you want to actually see Steve and Pierre right by that structure and test it with them, well, I don't test it with them, just look at it. But you could buy a beer. I think the bar's still open, and I'm sure Jit's very happy to share. There's an incredible amount of knowledge there that I feel we're just scraping the surface of, and let's get some more of it. So thank you all for coming, and do come to the rest of the talks and series. Thank you.